Okay, in Calculus 173, we started talking about pressure. And what are the units for pressure and what does it mean to have pressure? Okay, so pressure. Some people said, well, tire pressure is in PSI. What's the P, S, and I stand for? What stands for pounds per square inch, or inches squared. Pounds is a measure of what? Well, if you put the scale between you and the earth and read the dial on it, it measures how much the earth is pulling on you, or you're pulling on the earth. You're pulling together, so it measures the force between you and the earth. Pounds is a measure of force. Okay? Now, what's force in the metric system? Well, this is caused by gravity. Now, your mass is attracted to the mass of the earth, and if you take it times acceleration due to gravity, your mass in kilograms times the acceleration due to gravity, which is 9.8 meters per second squared. Kilogram meter per second squared is a newton. So 1 kilogram is 9.8 newtons of force. So there's newtons. So pressure in the metric system is going to be newtons per, say, meters squared. Now, there are other measures of pressure. There's barometric pressure, which is just a brief explanation of that. If you take a tube, long tube, very long tube, fill it with water, and the bottom is closed, so it's more like a very skinny cup. You fill it with water, put your finger on the end, flip it over, and put it into a tub of water, closed on the end. It's filled up with water, and stick it into a tub of water. The water will try to fall down, but you won't see it fall down at all. Now, if you happen to do this same thing with mercury, which is 14 times more dense than water, same amount of mercury weighs 14 times as much as water. You do that and tip it over, it'll pull down to 760-ish millimeters of length, 0.7 meters. They'd leave a space up here, which the guy who first discovered this, doing mercury, probably ended up with mercury poisoning, which makes you go crazy or makes you mad as a hatter. Hatters use mercury all the time to make hats, and that's where that phrase "mad as a hatter" comes from. They went crazy from mercury poisoning. But he created what was considered the first vacuum. Mercury was heavy enough to pull down and leave space in the tube that had nothing in it. Maybe perhaps a few vapors of mercury, but Basically, that's the first vacuum. He carried this around with him and took it up mountains and discovered that it changed when you go up mountains, the height of this. He also watched it, and as the weather changed, it went up and down. And then he noticed a thunderstorm coming, and it went way down, and then lightning happened, and he saw sparks going there, and he discovered first example of having a plasma type thing, but they didn't know what that was. But anyway, sparks happen in this vacuum. That became the basis of barometer, because when you go higher up, there's less weight of air sitting on this, so this tub isn't pushed, the mercury here isn't pushed as hard, and so it goes up, which causes the mercury to drop. So a falling barometer means we've got less weight of air. A warm air mass expands and the mercury falls. So it means we have a warm air mass. And if we have a cold air mass, which the air is condensed, makes it heavier, pushes harder here, and the barometer goes up. Cold air masses tend to be more stable air. Warm air masses tend to have more moisture and rain and unstable, and so this can be used to predict weather a little bit. That's what a barometer is. So you can measure pressure in millibars. That's a common one. Millimeters of mercury is a millibar. You can measure pressure in atmospheres. If you go to Europe and ask to put air in your tires, they will ask you, well, atmospheres. How many atmospheres do you want? Well, one atmosphere is at sea level. Generally, it changes because of warm air masses or cold air masses. It's how much the weight of air is pushing on you. Okay? So, pressure. We're going to focus on pounds per inch squared or Newton meters. Newton meter squared. Newtons per meter squared. Pressure. So, what I started this in the class was, what if we had a dam between a mountain? We had a trapezoidal dam and another mountain, and it's holding back a lake. And there was a pipe through the dam. So looking at it, the side view, my dam might look something like this. And there's a pipe through the dam, and there's water behind the dam up here. And if that pipe was 200 feet down below the surface of the water, and the pipe comes through the dam and it's capped and there's a pressure gauge on it, or what if we had just a piece of pipe with water filled up to 200 feet above where a pressure gauge is? Both of these are 200 feet. I asked the class which one would have the higher reading. The one here where all the water behind the dam is pushing on this, or just the water, this vertical column of water pushing on it. And there were some students who had had physics before and knew the answer to this. If you think about it, it seems like all the water behind the lake would be pushing harder. But the pressure depends only on how deep you are in the water. The deeper you go, the more pressure. The less deep you go, the less pressure. It doesn't matter whether you're in a little swimming pool and go 8 feet deep, or you go into to a lake and go 8 feet deep. The pressure is the same at 8 feet deep. So how much is the pressure? So if you're in water, how much does water weigh? because it's the weight of the water sitting on top of some area that determines the pressure. So, in the metric system, 1 gram of water weighs a mass of 1 gram of water is 1 centimeter cubed. 1 cubic centimeter. 1 milliliter of water is 1 gram. So that means that how many kilograms are in a meter cubed of water? Well, to change grams to kilograms, we have to put grams down here, and there's 1,000 grams make 1 kilogram. And there are 100 centimeters in a meter, but we've got cubed, so we're going to have to do 100 cubed centimeters cubed in a meter cubed. It's 100 by 100 by 100, which is 100 cubed, or a million. So 1,000 goes into a million 1,000 times. So then we've gotten rid of the centimeters. We've gotten rid of the 1 kilogram is 1,000 grams. So we got rid of the grams, and we got, there we go. So we got 1,000 kilograms of mass of water in a meter cubed. But to get it to be newtons of force, we have to take the kilograms times meters per second squared. So the weight of 1 cubic meter of water is times 9.8, or 9,800 newtons per meter cubed. So this is density of water. This is density of water, mass density, mass density. This is weight density. So this is the weight density of water. Wood density is a little less. Weight per meter cubed of wood. Mercury is 14 times as heavy, 14 times this number of newtons per meter cubed. Mercury is very, very heavy liquid. Gold has a very high weight density, a lot more times than this. Oil, which floats on water, is a little less weight density than this. Now, this is in the metric system, but I am proposing a problem here in feet in the English system. So I'm just going to tell you that if you go through the conversions for how many newtons or how many kilograms is a pound and do all the conversions, you end up with the weight density in the English system of 62.4 pounds per foot cubed. A cubic foot is 7.5 gallons roughly. A 5-gallon bucket then would weigh less than 62.4, and it would weigh 5 over 7.5. Nope, 7.5 over 5 over 7.5 times this, smaller. But there is the weight density of water in the English system, measured in pounds. So, at 200 feet down in the water, if you multiply this by 200 feet, one of the feet cancel, and you're going to get pounds per foot squared, which is what pressure is measured in. Over here, it was pounds per inches squared. Pounds, force per square unit, square area, per area. Here we have force per area. And it's, so at 200 feet, if we multiply 200 by that, 200 times 62.4, the pressure on every square foot. So if this was the bottom of the ground on the underneath the water's going to push with 12,480 pounds on every square foot. Well, how many PSI would that be? So we'd have to change, if we have 12,480 pounds per foot squared. We have to change the foot squared to inches squared to figure out the PSI. So foot squared, we want to cancel, so we put it up there. We want to put inches squared here. And 1 foot is 12 inches, so 1 square foot is 12 times 12, or 144 square inches. So if I take this divided by 144, at 200 feet, the water pressure is 86 2/3 PSI, pounds per square inch. Okay? So at 100 feet, half of that, it'd be half the pressure. We'd be multiplying by 100 instead of 200. So at 100 feet down, the pressure is 43 1/3 PSI. That's kind of a nice number to remember, especially for me when I'm doing my irrigation system. There's a canal up by my place that's about 80 feet above where I have my sprinkler systems in my hayfields. So if I had a tight pipeline all the way to my sprinklers, how much pressure would I have? Well, if it was 100 feet, I'd have 43. At 80 feet, I'd have 8/10 of that. I'd have 70 pounds of pressure. 70 pounds of pressure would just barely run the sprinkler system. I like to have about 100 PSI to run it well. So, and there's usually some friction for getting down here, so in the pipes, so that lowers the percentage. So it doesn't work real well just to use gravity. And I have some hayfields not all the way down here 80 feet below. I have some at 40, and that's not enough pressure to run the sprinkler system. So I have to up the pressure with a pump. Okay? So, where's calculus come in all this? Well, let's go back to my dam. Let's say the dam was 150 feet across here and 100 feet across here. How much is the water pushing, if it's 200 feet of water, well, maybe this should be 250 feet because it's wider than it's tall here. And this might be 200. Let's do that. How much force is pushing on the dam from the water? If you're worried about pushing the dam out of the way, we got to make it so it can hold that much force. So, since the pressure is getting more and more and more as we go down, at some depth, there'll be an area that the water is pushing on. And the pressure at that depth, if I do it in feet, will be 62.4 times how far down it is. That's the pressure. And the pressure's in pounds per, if I take it times the depth, that's going to cancel one of the feet in this. And so it's going to be 62.4 pounds per square foot, because I'm taking it times the depth, feet. I would then have to multiply it by the area that it's pushing on. And so now let's see if we can figure this out. We're going to figure out how hard it's pushing on this strip and all the other strips from the top of the water down to the bottom. It's going to push there's a bigger area up here, but it's pushing very little up here. Down at the bottom, it's pushing pretty hard, and the area is a little bit smaller, but whatever. So we need to set a coordinate system on here. And you can do it pretty much wherever you want to put the coordinate system, but I'm going to make the suggestion that we set a coordinate system where the y-axis is up and down. This is what the class wanted to do, so I'll put it up and down. And the x-axis could be at the surface of the water, or it could be at the bottom of the dam. We could put it other places, but those are the two most common, or we could put it at the surface. We don't know how far it is to the top of the water from the top of the dam, so probably wouldn't want to put it there. So, how do we decide? Doesn't matter. Let's start with it here. Then I'll switch color and do it someplace else. So, this distance, let's put a point here. Its coordinates would be x and y, where x measures from the y-axis over to this point, and the y measures this way from the x-axis. Okay, so we have 62.4 depth, well, that's y, and the area is, this area, which is a slice that's really short in height. That's a dy. Height times the length. Well, if I put this in the middle and this is x, the whole length is 2x. So I've got pounds per cubic foot times feet times feet times feet. So I get pounds, which is a force. That's what we want to know. How much force is there on the dam? And we want to add them up for this strip and all the strips from the bottom to the top, or the top to the bottom, either way you want to go. So it'd be from y going from negative 200 to 0. So let's work that one out. Oh, wait a minute. Y, x. We're going to have a problem here because we can't do an x. It's got to be in terms of y. Well, notice that this is a line. We're going to assume that it's a straight line pushing against a mountain. Whenever they built it, made a straight line. So we've got to come up with an equation for this line to relate the x and the y. So what's this point? Well, this is 250 feet, so this is 125 feet over, and it's up and down 0. What's this point? Well, it's 100 and negative 200, isn't it? So what's the equation of the line? Well, the line would be y equals, let's see the slope. Change in y, let's go from here to here, that's 200. Goes up 200 as it goes up 25 times x plus a y-intercept. Well, 200 divided by 25 is 8. So what's the y-intercept down here? Well, here it is over at 125. If I go down 200 feet, it goes to 100. So I got to go over some more times. Let's see. I lost 25 feet in 200 feet. And I have to lose 25 feet 4 more times, so I have to go 200 4 more times. So that's 5 times 200, or 5 times 200 is 1,000. So there's the equation of the line. And I need to get rid of the x. So I would go y plus 1,000 equals 8x divided by 8. And that's what I would use for my x. So to figure out the force on this dam with the coordinate system at the surface, it'll be the math integral from negative 200 to 0 of 62.4. I could have put that on the outside because that's a constant, and I could have put the 2 on the outside, but I'll just leave it in there. Y. I'll actually use y just so it looks the same way. So where's y? Y is down here. Alpha, that's second. Alpha y times 2x, and x is going to be y plus 1,000, and I have to put that in parentheses, divided by 8. So there's the x, there's 2x, that's 6.2 y, 2x dy. So now I got to go out here and put dy. And it says I'm going to have, pushing on my dam, 10,400,000 pounds of force. 1.04 times 10 to the 7th pounds of force. Okay. Now let's put the coordinate system at the bottom of the dam. So let me see if I can find a different color pen so we can see the difference. Is this one blue? Yes. Let's put the coordinate system down here, where this is x and this is still y. So we're going to do the integral. It's still going to be a dy because y is still up and down. And y is going to go from 0 to 200. And it's still 62.4. And the depth, well, depth of the slice is from the surface to the slice. Y is now this way. So the depth would be 200 minus y. So that's the depth. Before, with the coordinate system here, that was y. That's how far down it was. But now we're going from the bottom up. This is y, but that's not the depth. The depth is from the surface down, so I have to take the 200 minus y. And then I have to do, I got the thickness of this, and the length of it is 2x. But now my equation for x is not this one, because now the points are, this point is 125 and 200. And this point at the bottom of the dam is 100 in the x and 0 in the y. So now it's 100, 0. So my new equation is, well, the slope is still 8. Goes from 0 to 200, which is 200 over the change in x, which is 100 to 125, 25. So that was the 8x plus the y-intercept. Well, I am down 200 feet, so this is going to be only 800 feet instead of 1,000 feet. It's at minus 800 feet because I started 200 feet lower, and it goes over 25 feet. Every 25 feet, it goes down 200. That's what this said, down 200 feet over 25, and we got to go over 4 more, so it's going to be down 800. So if I solve this, I get y plus 800 divided by 8 equals x. So I'm going to put this in place of the x and 200 minus y in place of the y. So I'm going to pull out the calculator and do the same integral, except now I got to go back and say it's y it was supposed to be y plus x was y plus 1,000. So I got to insert a 0. I'm missing a 0 in that original one. Okay, and why did I get a minus number? Well, let's go back and look at that. This should have been 1,000 because we added 1,000 to both sides and divided by 8. So it's y plus 1,000 divided by 8. And I measured my depth. If this is 0, y is a negative number. And so that makes it wrong, and we needed to change the sign on this. So I should have either switched my limits or changed that. So the answer is not this. The original answer should have been 22.7 times 10 to the 3678. That many pounds of force. Yeah, see, if you make an arithmetic error or error on here, you could get a dam that was built that wouldn't hold the real force. Would have been too light. Would have broken. All right. So now let's do it this one. So it would be, come back here. Now we're going from 0 to 200. 62.4 times the depth was y, but now we got to go parenthesis 200 minus y, close parenthesis. So instead of just y, it's 200 minus y, 62.4, 2 times x, so there's the 2, and my x is now y plus, not 1,000, but 800 divided by 8 dy. So that's this one. And hopefully I'll get the same answer, only positive this time. Same answer, but positive. So the problem with the first one coming out negative was because the depth was a negative amount, so I needed to change the sign on the depth so that it's a positive amount. The depth from there to there that works out. And so there's the pressure on a dam and how calculus is used to calculate it. Okay? And then we're going to talk about work next in class.